Oh, welcome back, Idiot Squared viewers. Today we have a massive mind-bending episode. We will be discussing reality, the nature of reality, what it means to exist in this universe. What could the universe be? How can we model it? Among many other things, we're going to be discussing infinity one toposes, infinity groupoids, a whole bunch of crazy mathematical concepts. And a lecture given by Jonathan Garrard in regards to the Wolfram Physics Project, which promises to be a theory of everything in a sense. So stay with us, stay tuned. We're going to dive deep into this, and we're going to do an idiot's exploration of this. Polska, I sent you a video. I sent you some stuff to read over. What did you think of it? Did any of it make any sense?
So this is actually take number 2 for us. This is the second time we're going to try and sort of hit this home. It's a heavy fucking topic. It's real heavy. I didn't really understand it too much the first time around, so hopefully I get it a little bit better this time around. I didn't watch the video just because, I don't know, there was something, the audio was just annoying me for some reason, and I wasn't following. It was difficult to understand. But the document you did send me, I thought it was really interesting. So basically what you did was you took the transcript from that 2-hour video, you uploaded it into Claude, the AI training model. Is that right?
Yeah, Claude's an AI.
Yeah, and then basically you just started asking it questions about the transcript to try and sort of clear things up and, get a better understanding of the topic. And I thought it was really cool. I read through all of that, was pretty lost, found myself looking in the dictionary every couple of words. But I'm here to learn, bro. I'm hoping that you can, sort of gear this ship or steer this ship into the abyss, and I'm ready to roll, guy.
All right, that's good. So what I think is the best way to sort of start this is starting from like the highest level possible, so we can sort of get a big top down view, and then we can sort of weave these concepts together as we go through. So broadly starting, like, we exist, right? We have experiences, we have memories of things, we can do things, we can act in this giant thing that we call the universe, right? We have space that appears to be 3-dimensional, 4-dimensional if you include time, and we as humans are trying to sort of understand this. We're trying to make sense of it all. Like we can develop these models that make certain predictions, and up until now we've had 2 theories that appear to be disconnected, but they explain things very well. So at the high level, at the scale that we exist, and at the cosmic scale, we have general relativity. And at the lowest level, we have quantum mechanics. But historically, these 2 things don't seem to match up, right? There seems to be a disconnect between the 2. And so, like, that's what we've done so far as humans. But in no way has it been a complete theory. In no way has it been a complete understanding of the universe, of reality, of everything else. And so the Wolfram Physics Project has tried to resolve these things. They've come up with a novel way of, I started with this. Typically, we think of space-time as being continuous, right? It's continuous. That's the easiest way to say it. And what the Wolfram Physics Project and by it being continuous, right, it leads to certain problems when we try to model things. Okay, so we end up with these big infinities, we get ultraviolet divergence, we get problems. Okay, so it doesn't match up. And at the quantum scale, the quantum means quanta or discretized. And so the Wolfram Physics Project has gone with a different approach, and they've modeled the universe as being fundamentally discrete, which means small part. There is a smallest unit that there can be. There is a smallest thing that there can be. Right? And so it's not continuous, but it's discrete. Now, they've had amazing success. They've been able to derive general relativity, special relativity, quantum mechanics, quantum field theory out of their models. And they use these things called hypergraphs, right? Now, we're going to do a zoom out. That was a little zoom in. We're going to do a zoom out. So we have ways of describing things. So we have geometry and we have algebra. So algebra is kind of like from discrete things, building things up, and geometry is kind of looking at continuous things or big things. Whenever we have too many parts to count, we kind of use geometry. Now, this Wolfram model, like I said, they've been able to derive these things, but it's provided a fundamentally different perspective, okay? So Gerard gives this amazing series of talks for the SEMP 2023 summer school. And in his final one, he links all these things together and has this big overarching sort of series of statements and explanations. And he links all of this stuff together in such an amazing way that it can fundamentally change how we perceive the universe and how we understand the universe. And I think it's very powerful. So we're going to kind of jump into that, right? So I'm just going to give a quick sort of little couple of takeaways from the talk, and then we can sort of jump into some of these concepts and do that top down sort of view. So in the lecture, Gerard weaves together rich connections between category theory, computation, causality, and physics that suggest fundamental relationships. The conceptual arguments point toward profound implications and research directions following further rigorous development. Gerard introduced the concept of multi-way systems, which generalize computational processes to allow for non-deterministic branching evolution. He related these to symmetric monoidal categories. He discussed how hypergraph rewriting naturally gives rise to dagger, compact, closed, symmetric monoidal categories, which have structure to omit a quantum mechanical interpretation. So just to stop on that one point, dagger, compact, closed, symmetric monoidal category is a whole bunch of words that essentially means that you could have like local time reversibility in quantum mechanics right down the bottom.
Like time travel?
Yeah, at the tiniest scale, little bits of time travel are possible, but at a big scale, no, they're not. So Gerard explained how the complexity of state evolution and state equivalence are dual under an adjoint functor relationship. He related state evolution complexity to computational irreducibility and state equivalence complexity to multi-computational irreducibility. He proposed that the obstruction to parallelizing sequential processes reveals causal relationships between them. This gives a general definition of causality that encompasses various formalisms. That point right there is huge, and we're going to try and untangle a bit of that later on in this pod. But he's come up with a new way of defining causality or thinking about causality, which is fascinating. Gerard speculated about covariant computation, which generalizes computation by incorporating space-time and branch-time covariance effects. This relates to his idea of causal multi-way systems. He discussed how taking infinite categorical limits gives rise to infinity groupoids, which by Grothendieck's hypothesis induce spatiality and topological structure on lower dimensional categories. This provides a potential origin for laws of physics. So overall, Gerard explored connections between category theory, computation, causality, and fundamental physics, proposing some speculative ideas about how they may be unified through an overarching multi-way system formalism. And the implications are philosophically profound, but require some further mathematical development. So that's just, in my opinion, this is amazing. I don't know if any of that meant anything to you, but it's pretty huge, in my opinion.
I mean, just because we talked about this before, some of it does, but it's heavy, man. I mean, I think you know how heavy it is. So I'm trying to hang on here, and I'm hoping that more of this becomes more clear to me as this podcast moves forward, guys. So let's keep trucking along.
Okay. So let's start with a few things. We've discussed this concept of the Roolyad that emerged from the Wolfram Physics Project, which is essentially all possible. The Roolyad is all possible rules run in all possible ways. Right? That's one way that they describe it. In this presentation, Gerard defines it more rigorously. And so instead of the Roolead, well, the Roolead is an infinity groupoid, right? So an infinity groupoid is this mathematical construction from category theory, and that is the Roolead, okay? But the Roolead or the infinity groupoid exists within an infinity one topos. So think about like if we live in the Roolead, that's our universe, but our universe exists within this bigger space, this infinity one topos.
Infinity one topos?
Yeah, correct. Now, I'm just going to share something with you quickly. So this will be a nice little, well, it's a terrible depiction, but excuse my drawing skills.
Okay, so far I'm understanding that the Roolead exists in the infinity one topos, but I don't even know what that means. Like, what is the infinity one topos?
So it's a classifying space for infinity groupoids. So I don't know if you can see my screen. Do you want me to make it a bit bigger?
Like we have no, that's good. I can see it. It looks like an atom.
Yeah, well, so that's just because of my bad drawing. But essentially think about it like this. So you have this infinity one topos, right, which is this big classifying space. And within that, you can have these different infinity groupoids, okay? So it's like a subset of it. And then within the infinity groupoid, you have these Roolean multi-way systems, okay? So you have all these different Roolean multi-way systems. All of those combine to form an infinity groupoid. And within those Roolean multi-way systems, you have hypergraphs and branchial graphs and all these different graphical, graph-based structures, right? That we can now use to model. So just a little explainer on some graph-based stuff, right? So typically in general relativity, we talk about Riemann manifolds or Riemannian manifolds or Riemannian manifolds. And that's what we generally refer to as space, right? And then we have Lorentzian manifolds, and we typically refer to them as space-time. And so in this model, a Riemannian manifold is modeled by a hypergraph, right? So it's a minimal model for space. And then a Lorentzian manifold, which is space-time, so space plus the progression of time, is modeled by a causal graph. Okay, so that's a minimal model for space-time. And then we have a multi-way evolution graph, and that equals a projective Hilbert space, and that's how we typically model quantum mechanics. Okay? And then we have branchial graphs, which is equivalent to quantum field theory in the infinite dimensional case and quantum information theory in the finite dimensional case. So these are all different graph ways of looking at graphs and different graph structures. And this is how they relate to our current understanding of things in general relativity, special relativity, quantum mechanics, etc. Okay? So just when we're talking about this, so in this infinity one topos, there can be many different infinity groupoids. And I'm pretty sure that there can be many other infinity toposes. So it's kind of like this nested fractal that we sort of exist in. But if you imagine in this big infinity one topos, we have many different infinity groupoids, okay? We exist in one of these infinity groupoids, okay? And in that infinity groupoid, you have many different Roolean multi-way systems. So we exist somewhere within that. We're sampling a little subset of these larger spaces. Does that kind of make sense?
Yeah, I just don't understand how, I understand that the universe exists in the infinity one topos, but what does the infinity one topos exist in then?
So think about, So this brings up some philosophical questions, right? So how do you get something from nothing, or, that kind of thing? What does the universe exist in, right? Well, so interpreting it this way, we sort of come to this conclusion that anything that can exist does exist. So all that's possible that could be in any possible way is. And then we exist as a subset of that. So we exist as one way of being within that, or one series of rules, or one collection of different rules within that space.
Okay, so in this schematic, there's essentially no beginning and no end, right? time ceases to exist.
But well, potentially, depending on your perspective, right?
Okay.
So for us, it does, right? But from like a super bird's eye view, if you could exist in outside this infinity one topos and look down on it, then that would just be it. If that kind of makes sense. So the sort of philosophical thing here is people are like, why does anything exist? And then, people's answer to that is that existence is the default.
So are these subsets moving within each other and multiplying or collapsing? How are these each subsets moving within each other or within the infinity one topos? And is the infinity one topos expanding, or is it, man, it's hard to know how to ask these questions.
It just is. I think that the answer to that is it just is. And it's in unbelievably humongous. Like we couldn't even comprehend the size of these things, right? Like if our universe is just some little point in here, like our universe is just some little point within all of this, it's just so big, right? But all we can really talk about and do sort of experiments with is stuff to do with ours. So we can see like, okay, well, based on what we can measure and observe and different things, what can we say about this space, so to speak? Okay.
If our universe is expanding, is this entire infinity one topos also expanding as well?
Well, I don't think so, because I think that it is all that can be. So it is maximal in that regard.
Like it's like infinity.
Yeah.
So it's never ending.
It's just all that there can ever be.
I'm trying to like picture this in my brain, and my brain is melting.
Yeah. We're very computationally bounded, so it's very hard to model infinity in a finite brain. Okay, so we sort of get that nested structure.
Yeah, I kind of feel like there's a little bit of faith involved here. You know what I mean? Like this is almost like, I don't want to say religious in the sense, but there is a part of this that I feel like that. I mean, there's things that we are unable to explain, and we just have to sort of accept this sort of hypothesis that Wolfram and Gerard, right?
Gerard, yeah.
Gerard are putting forth. And it seems like, there's just things that we just have to sort of go along with so we can understand the rest of their argument. Do you kind of get the same feeling?
To a degree. I think so many things you sort of just have to start with a belief. And yeah, it is a bit like a religion in a sense, but the difference here is that there are ways of, sort of proving certain things, modeling them and showing that they are consistent, and that they link back to reality. So this is a model that seems to have amazing reach and seems to make sense of things that were typically very confusing or we had no other good explanations for, whereas this now provides and illuminates different explanations and good explanations that can be used and leveraged. So this seems to make sense of a lot of things that we've been very curious about before. If that kind of makes sense.
Yeah, no, that part does make sense. It's just because we're unable to measure some of these things. So it's really difficult to comprehend. That's where like the faith part comes in.
We can't measure these things in a way, but we can construct. So this is the craziest thing with category theory and topos theory, is that you can construct these objects. And the construction is actually fascinating. The construction comes out of these models. So utilizing these hypergraph multi-way system models, it shows how you can build these objects. You can build an infinity groupoid. Then you can build an infinity one topos as a classifying space for those infinity groupoids.
So we exist in the infinity groupoids, which is the multi-way, what is that, evolution graph?
Yeah, Rule or multi-way evolution, or Rule or multi-way system.
So that's where essentially we exist in, correct?
Yeah.
Okay, and then just outside that, we have the pink one, the pink portion. What does that say?
So that's a Rule or multi-way system. We exist in this Rule or multi-way system, or as a Rule or multi-way system.
We exist within that one.
Well, we exist within all of the, because it's nested. But where we are in that scale is we're somewhere down. Maybe the yellow one is more like the multi-way. We exist at like the causal graph level, so to speak. But we're made up of all these different subgraphs.
Okay, so we can't even begin to comprehend visually what it would be like to be in the pink portion. What is it called again? My bad, bro.
The Rule or multi-way system. That's where we are.
Well, but we're in the multi-way evolution portion, the yellow portion.
No. So, we might be going a bit. Okay, so we are made up of all these different subgraphs, right? All these different processes constantly evolving through. So we exist as like this tiny little, like imagine it like a giant ball of twine.
Yeah.
Okay. Or a ball of string, right? And then, so you have, we exist at some scale. So you have like the core of the twine. Okay.
Okay.
And then as you build it out, you get bigger and bigger radius, right? Diameter, all those things. Okay. So it starts to grow out. We exist as like a collection of fibers within that greater space.
Okay.
And if you imagine that that each one of those concentric circles is like, made up of series of balls of twine that are intertwined, and they progressively scale out in bigger and bigger scales. And so we exist as like a little subset of that.
Okay, I'm understanding that we exist in all of this, because all of this is sort of nested, like you said. Like, I think that's like a good word to use, that this is nested. However, our brains are only able to comprehend like the most basic structure here, right? Because we live in the multi-way evolution, essentially, don't we?
Well, we live within the infinity groupoid, but we also live within the infinity one topos. It's just that the scale is so vast, right? So we're sort of sampling at the level of causal graphs, right? Which is at the minimal model for space-time.
Right. Okay.
Yeah.
Okay. Yeah, that makes sense.
So, are you like? Do you want me to? I can give a bit of an explanation on the infinity one topos and a Grothendieck infinity groupoid.
All right. Yeah, I think that'd be a good idea.
Okay. So, an infinity one topos is a concept from the field of higher category theory, a branch of metamathematics. Category theory is a branch of metamathematics that deals with abstract structures and relationships between them. You can think of it as a language that helps mathematicians talk about mathematical concepts in a generalized way. A topos in category theory, a topos is a certain kind of category that behaves somewhat like the category of sets, which is a collection of objects. It's a playground where mathematical objects and their relationships can be studied in a very general setting. An infinity one topos is a generalization of the concept of a topos to the realm of higher category theory. It incorporates notions of infinity and allows for the study of more complex structures and relationships. So an example is, imagine you have a set of nesting dolls. A traditional topos might allow you to study the relationship between individual dolls, but an infinity one topos would let you study the entire collection of nesting dolls, including the relationships between the different layers of nesting in a more holistic way. Okay? So now we have a step down from that. We have the Grothendieck infinity groupoids. So a groupoid in mathematics is a concept that generalizes groups, which are sets equipped with an operation that satisfies certain properties. A groupoid extends this concept to include more complex structures. An infinity groupoid is a further generalization of a groupoid to include notions of infinity, similar to the infinity one topos It allows for the study of more complex structures and relationships. So Grothendieck infinity groupoids, these are specific kinds of infinity groupoids introduced by Alexander Grothendieck, a prominent mathematician. They are used to study geometric and topological properties of spaces in very abstract and generalized ways. So as an example, imagine you are studying a complex multidimensional shape like a fractal. A Grothendieck infinity groupoid would allow you to study not just the shape itself, but also the relationships between various parts of the shape, including how those relationships change as you zoom in to infinity. Yeah. So there is a relationship between these two things, like I mentioned, as shown in that diagram. I'll just, I'm going to leave that up. Yep. So homotopy theory, both infinity one topoi and Grothendieck infinity groupoids are central objects in homotopy theory, a branch of mathematics concerned with the study of spaces and their structures up to continuous transformations. Inclusion of concepts. Grothendieck infinity groupoids can be seen as being included within the framework of infinity one topoi. In other words, every Grothendieck infinity groupoid can be regarded as an infinity one topos, but not every infinity one topos is a Grothendieck infinity groupoid. So an example is, think of a Grothendieck infinity groupoid as a specific type of creature in a vast ecosystem, the infinity one topos. While all Grothendieck infinity groupoids are part of the ecosystem itself contains a variety of other creatures. So it's like we have our universe, right? But then inside the infinity one topos, there's a multiverse of other universes with other possible rules, with other different ways of being, existing, and things happening. So it's a way of formalizing this, multiverse concept. Yep. So the implications. So understanding the relationship between these two concepts is obviously important. So people typically use this framework of infinity one topoid to study Grothendieck infinity groupoids in a more generalized setting, uncovering new properties and relationships. That kind of makes sense. So these are structures that allow us to understand and develop ideas about these, about life, reality, the universe, existence, the multiverse, everything. So it kind of should make some sense there.
Yeah, sure. I'm just going to say sure.
So we've mentioned category theory. We've mentioned set theory. And so I thought I could just give a nice little sort of differentiation between these. So Gerard does a great job in his lecture of separating the difference between the two. So set theory is a branch of mathematics that deals with sets, right, which are collections of objects. Set theory forms the basis for many areas of mathematics and provides a foundation for mathematics based on the axioms like the Zermelo-Fraenkel axioms. Okay, so this is the foundation of modern mathematics. So some key aspects of set theory. Sets are simply collections of objects. For example, you could have a collection of objects like apple, orange, banana, which would be objects in the set of fruit. Yeah. You could have red, green, blue, yellow, which are objects in the set of colors. Yeah. Simple examples. So sets can be described visually using Venn diagrams. Shout out Kamala Harris, her favorite word, Venn diagrams, which show intersections or unions, right? So you could have the set of cats, and then you could have the set of black things. And where those two overlap, you end up with the set, you have a set of black cats. Yeah?
Okay, yeah.
Kind of makes sense? Okay. Yeah. So sets have elements. An object that is part of a set, for example, an apple, is an element of the set apple, orange, and banana. Yeah? So an element, we're talking about elemental particles, all that sort of stuff. An apple is an element of the set apple, orange, banana. Common set operations include union, intersection, complement, and subset. So category theory, on the other hand, deals not just with collections of objects, but also with morphisms between objects. Morphisms are often referred to as arrows. And the easiest way to think about this is just transformations between things or processes, right? Which represent structure-preserving transformations from one object to another. That's what a morphism represents. Okay? So some key aspects of category theory. A category consists of objects and morphisms, also called arrows, between objects. Morphisms allow transforming one object into another related object. For example, a morphism could transform polygon A into polygon B if B is just a rotated version of A. Morphisms can be composed if you have morphisms. If you have a morphism F that transforms A into B, and morphism G that transforms B to C, you can compose them to get a morphism from A to C directly. So one example of this a good example of this that I can provide you is, so if you have oh, that just froze on me. Think about like if you have a process that goes from A to B and from B to C. In category theory, it says that there's also a process that can take you from A to C directly. So instead of having to go through A, B, and C, right, you can go from A to C directly.
Okay. Teleportation?
Sort of, yeah. So think about like if you have your dad is your dad, okay, and your dad's dad is your grandfather. Okay, so it goes your grandfather had your dad, then your dad had you, right? So that's A, B, and C, right? Your grandfather's A, your dad's B, you're C, right? Well, there also exists a relationship between you and your grandfather, right? So you can go from your grandfather to you, right? And that shows the relationship of grandfather. Does that kind of make sense?
Yeah.
Okay. So this allows abstracting the commonalities between structures and transformations. A key difference is that set theory treats objects/states as fundamental, while category theory treats morphisms/transformations as fundamental. So set theory is all about the object or the state, right? Whereas category theory is more about the transformations and the processes. So how do those things relate to each other, or how do the transformations occur? Like what are the processes in that, right? So it's a different way of viewing it, but it's also a more sort of encompassing, holistic way that opens up a richness. So category theory is something that explains context, right? It gives context its meaning. It's the relationship to other things. Whereas set theory typically just looks at the object in isolation or in relation to other objects. Whereas category theory is more about the processes, those transformations, those morphisms. So an example in quantum mechanics, set theory focuses on the space of states a quantum system can be in, whereas category theory focuses on the transformations between states and the algebraic structure of how transformations compose. So category theory provides a more dynamic perspective focused on structure-preserving transformation. So it's just, it gives a new richness in the way that we look at things, right? So we can sort of see that because the foundations of mathematics were based on set theory, it led us to see things in a certain way, which was only part of the story. So an object and a state is part of the story, but it isn't the whole story. There's these processes, there's these transformations, there's these morphisms that happen. And by looking at it through that lens, it gives us sort of a richer view and a richer understanding of things. That kind of makes sense?
Sure.
So you could look at something, right? So you could, what's a good example? If traditional set theory thing, you're looking at a thing as an object, right? You're just looking at it. Whereas in set theory, you would look at how that object relates to other objects. You would look at how that object can transform or compose with other things. And then it leads to that richness.
Okay. So set theory is how objects are related to other objects, essentially, how they intertwine or how they communicate or how they're related to one thing and another.
No,
Is that right?
no.
No?
So set theory is about objects, and it can
What's
be,
that?
set theory is about objects.
Yeah.
So you have sets of things, and then you can have the overlap between them. So that, what do they have in common? Right. So you have that Venn diagram overlap, right? So yeah, correct in that saying,
Yeah.
but it doesn't really
Okay.
say anything about the processes. So it's very static. Think about it
Okay.
like very static.
Okay. Like the example you used, you have a set of cats and a set of black things. And when we have an overlap, we have a black cat, right?
Yeah.
Okay. And category theory is just the object itself. So what it could be an example of that?
No. So set theory is more like the object itself, whereas category theory is focused on the processes, the transformations, those morphisms. So it's like
Morphisms. Okay.
So think about it in terms of like, so it really simple way to think about it is like with graphs, right? So you think about set theory is just like, if you have a whole bunch of points, right, that are disconnected, they're just points, okay? That's like objects. And then as you start adding connections between them, they're like the arrows or the morphisms, and that's more of a category theory perspective, and then how that changes over time.
Could we say the sets are like the nodes and the lines between the nodes are sort of the categories?
Well, if you look at it as points and the arrows between them or the connections between them, then that would be a category theoretic point of view. So category theory is richer in that regard. It encompasses set theory. So you can have set theory. In category theory, set theory exists as the category of sets.
Okay. Yeah. I got you now. Yeah. All right, cool.
Yeah, kind of makes sense.
Yeah, no. I'm actually being serious. It doesn't make sense. Don't have to just rely on sure now. I can say yes.
Okay, cool. So in this Wolfram model, they use hypergraphs, which we've done a whole pod on before, right? Which is like you have again discretized space. So you have all these tiny little points, and they sort of estimate that there might be 10 to the 500 atoms of space, but it isn't a fixed quantity. Maybe it's expanding continuously, or maybe it is. We don't know. So hypergraph rewriting relates to advanced mathematical structures and has quantum interpretations, right? So hypergraph rewriting means defining rules for transforming graphs in multi-way connections called hyperedges, right? So already see how this is very categorical. This is very category theory. Yep. Okay, so for example, a rule could replace a set of hyperedges with a new set to model a mutation or a change. This is more general than standard graph rewriting, allowing for non-deterministic state changes. Okay, we can get into deterministic and non-deterministic in a second. In the talk, Garage shows how hypergraph rewriting generates fancy mathematical structures like that dagger compact closed symmetric monoidal category. The key one is the dagger functor, which provides a limited ability to reverse computations by running them backwards. So that's that very local time reversal that we were talking about that would allow like a very micro time travel to happen. But at the global scale, we sort of don't get the same thing. So this is being able to go back through a garden maze by reversing the directions you came from. So, and the dagger functor equips multi-way systems with some inherent time reversibility, right? That's all that dagger thing says. Okay, so with the additional mathematical capabilities from hypergraph rewriting, multi-way systems become sufficiently advanced to interpret in quantum mechanical terms. Quantum phenomena involve reversible state changes modeled by the dagger functor. So the rich structures of hypergraph generated categories support describing multi-way systems as abstract quantum computational processes. So this is how they model quantum mechanics, essentially using these hypergraphs or multi-way evolution graphs specifically.
It doesn't really sound like Wolfram and Gerard are hypothesizing that time travel can be a thing. Are they sort of closing the door on that idea in some ways?
At a macro scale, yes, but at a micro scale, no.
So what do you mean? Like,
so down at like, we're made up of or like different organs, which are made up of cells. Cells are made up of molecules. Molecules are made up of atoms. Atoms are made up of protons, neutrons, and electrons. They're made up of strange quarks, up quarks, down quarks, that whole thing. And so we exist across all of these scales. So at a very small scale, time travel is possible.
Like at atomic level?
No, below that. At the quantum mechanical level.
Okay.
Yeah.
Okay. What's the use case?
Well, we don't know yet, guy. We don't know. We're just saying that, like, this is that the models show that this is a thing. So if you could, if you were sufficiently computationally capable and advanced, and you had the ability to do this, maybe you could take advantage of that micro or that very local quantum mechanical time reversibility, and then maybe you could do some sort of time reversal at a larger scale. But it would require, like, a lot of computation and energy and action and all the rest of it. We don't know if that's possible, but there is some time reversibility at the base level, which leaves the door open, so to speak.
Okay.
There might be some way of doing it, and utilizing that phenomena at the low level to then make it happen at the high level. But I would think it's highly unlikely.
Okay.
Yeah.
Gotcha.
Okay, so I'm just going to do a brief sort of overview of some of the concepts from category theory, just so that we can sort of have some general ideas in our mind. So yeah, categories are just, you think about them as a collection of objects and processes that transform those objects, right? So as an example, the category of graphs has different graphs as objects. The processes are functions that map one graph to another graph by adding or removing edges and vertices. Okay, so it's just a way of transforming things or mapping them from one thing to another thing. So it's like a path from one place to another place. Morphisms. The processes that transform objects in a category are called morphisms or arrows. Continuing the graph example, each function that maps a graph to another graph by editing it is a morphism in the category of graphs. Okay, so it's a process that can happen. Composition. Morphisms can be composed by applying one after the other. If we have a morphism F that adds an edge to a graph, and morphism G that removes a vertex, applying G after F composes them into a new morphism that first adds the edge, then removes the vertex. Okay, then we have an identity morphism. So for every object in the category, there is an identity morphism that leaves it unchanged when applied. It's like a do-nothing process, okay, but it provides an identity to that object. Monoidal categories. These are categories with a tensor product operation that combines objects. For graphs, the tensor product joins two graphs by connecting matching vertices. This models non-deterministic branching of processes. Functors. Functors map between categories by transforming objects and morphism. A graph functor could map graphs to vector spaces by representing each graph as a vector of its vertex counts. Functors preserve the structure like composition, right? So imagine you have a category of stuff over here. You have a category of stuff over here. You can have like a transformation between those two. That's called a functor that preserves the compositional structure from one to the other place. So we're already sort of getting out in this nested pattern. So see how at the base level, they're called morphisms, but then between categories, they're called functors.
Okay. Gotcha.
Yeah. Adjoint functors. These are paired functors that reverse the direction of morphisms in a complementary way. They often arise between structure-preserving, symmetric monoidal functors and more general ones. So it's sort of like so paired functors. So a functor is that transformation, like, so it's like a morphism between categories.
Yeah.
Yeah. And then an Yeah, an adjoint functor allows for there to be a reversal. So when you do that across, there can be a reversal.
Okay. Okay.
Yeah?
Yeah.
Higher categories. By treating morphisms as objects, okay, so the morphism is that arrow. So say you have two objects and you have an arrow between them. Two objects and you have an arrow between them. A higher category, you can treat the morphism, that arrow, as an object. And then you can add morphisms between morphisms. We can build up a higher dimensional category with deep connections to topology. Okay, so this is how you build these groupoids and these infinity groupoids and the toposes, right? So say you have a collection of objects and you've got the arrows between them. So then if you think about it, you go, okay, well, I want to think my arrows, my morphisms, I want to consider them as points. And I'm going to draw arrows between the arrows, which are the points now. Does that kind of make sense? So you think about it like a cross-hatching, right? So you got a bunch of dots on a page, you draw a couple of arrows between those dots, and then you start drawing arrows between the arrows. So from one arrow goes to a different arrow. So instead of going to the objects, it's going to arrows now. Okay? So by treating morphisms as objects and adding morphisms between morphisms, we can build up higher dimensional category structures. And then we have infinity categories, okay? So by taking the infinite limit of this, so by just doing this to infinity, right? It leads to infinity categories where morphisms have all higher dimensions. Strange and abstract, they reveal surprising links between computation, causality, and the physical laws. This is what Gerard has said, and this is how we can sort of come up with that visual that we had before about the groupoid existing within the infinity topos and the multi-way systems existing within, or the Rullial multi-way systems existing within the groupoid. Crazy, right?
Yeah, my brain's melting, bro. So I'm hanging in there, but yeah, it is crazy.
Okay. So do we want to sort of get into multi-way systems a little bit? All right. So standard, what is a multi-way system? Do you kind of have an idea of what a multi-way system is? Remember we used the games example before?
The what example?
The games, when we did tic-tac-toe?
Yeah. So you can, I remember. So the multi-way system branches out and then it branches in. Or not branches in, but it collects in, right? Is that essentially what it is?
Some things can merge, some things branch.
Converge, that's it, yeah.
But remember, so in that example of it, tic-tac-toe, there's just those different possibilities, right?
Yeah.
Yeah?
Yeah, I remember. Yeah.
Okay. So multi-way systems kind of says it in the name. Standard computational models like Turing machines, which is what our computers are utilizing that concept, involve deterministic sequences of states where each state evolves to a single next state. Right? So we have like logic gates where you put a certain input in and you'll get a certain output out. Right? So we have like and, not, or, XOR, those different things. They're all examples of like, standard deterministic sequences. So you put a thing in, you're guaranteed to get a thing out or a certain thing out. Multi-way systems generalize this by allowing branching evolution. So each state can evolve into multiple possible states, like a branching tree.
Okay, so this is sort of like evolution.
Correct. That's one way to think about it, definitely. So this better reflects reality, where processes often branch into different possibilities instead of following a single linear sequence. So here's I don't know how you knew this, but my example is about evolution. So for example, evolution of biological organisms involves branching into different genetic variations versus a single linear progression, and making a decision branches future possibilities. Okay, so these are systems where a process can evolve in multiple possible ways, splitting into different branches. They can be visualized as graphs, with each branch showing a possible evolution path. Okay, so we have two different kinds of these things, right? So we can have tree-like multi-way systems, and then we can have non-tree-like multi-way systems, right? So in a tree-like multi-way system, if the multi-way system is tree-like, it means there is no merging/gluing of branches. So everything just keeps branching out. Like, so you start at a single point and then it grows out like a big triangle. Yep.
Okay.
Each branch splits but never reconnects with another branch. This gives us that tree structure. Okay. So then you can have multi-way systems that have this merging, okay, which is a different thing. So that never merging has a relationship to Cartesian products, which we'll discuss in a second. So when you combine two tree-like multi-way systems in parallel, this gives you a Cartesian product. Since the branches never remerge, the systems don't become entangled or interdependent. You can later separate the systems out neatly, which is the hallmark of a Cartesian product. Okay? So because they don't have that branching, there's none of that sort of confusion or the gluing or the cross, like the entanglement doesn't happen. So they can be easily separated again. So you can put them together, you can see what they do, and then you can pull them apart again.
Okay.
So they don't get knotted up, so to speak. So then we have the different multi-way systems that have this merging phenomena, okay? So that's like gluing the branches back together. So if the multi-way system does have remerging of branches, it means different evolution paths become connected. This is like gluing different branches together. And so this has a relation to a Kronecker product, right? So we have the Cartesian product, which is separable, and then we have this Kronecker product, which is not separable. And this is where, as Gerard explains in the lecture, this is where all the weirdness from quantum mechanics arises. It's from this thing. And we've always thought quantum mechanics was super weird and strange or whatever, but it's actually becomes quite simple if you think about it in these terms. So when you combine multi-way systems with gluing of branches in parallel that have that merging capability, it gives you a Kronecker product. Side branches can reconnect. The systems can become entangled, right? So we've heard of quantum entanglement. So this is what gives rise to quantum entanglement. So if you try to separate them later, you cannot do so neatly. This non-separability is the crucial property of Kronecker products. So in summary, tree-like multi-way systems combine to give Cartesian products, while multi-way systems with gluing of branches give Kronecker products when combined in parallel. This directly mirrors the separability versus non-separability of classical and quantum combinations. So in our game example that we did a few weeks ago and in our initial episode, we went through the tic-tac-toe stuff. And so how you could have a few different paths that would branch off, but then they would all end, or some of them would end up in the same game state or the same board state. That's like that sort of re-gluing.
Okay.
So different paths can lead to the same outcome. That's that merging. So you have the branching and then you have the merging. When you have that, you have a Kronecker product, which means you can't separate it easily. But if you don't have that merging, if you just have branching, then you can easily combine it and pull it apart again.
Okay.
Kind of making sense?
Sure. I'm going to go lean back on sure, guy.
Okay, so let's just take a pause moment and let's just have a look. So we sort of said that we have these graphs that we can start with, right? Which we can think of as points, and then we can have connections between those points. Yeah. And what changes the graphs are these rules, right? There's just these rules that exist, and that's different rules in different rule multi-way systems. So one rule multi-way system might have some collection of rules. A different rule multi-way system might have a different collection of rules that changes the way that the hypergraph updates or changes with the updates, right?
Okay. Mm-hmm.
And so these things they're doing their stuff, right? And from that, our universe emerges. Reality is what we perceive it to be.
Right, yeah? Right.
And then all of this exists within these higher spaces, these higher categories, these topoi, these higher, like the meta mathematics, and then meta mathematics.
So you think like other dimensions or other universes have a different set of rules?
Yes, that's definitely one of the implications for this. And there's different spaces in rulal space. Like there's a space of rules.
Okay, so the way that we understand biology and evolution might not actually occur in other dimensions or other universes then, if they're
Correct.
under a completely different set of rules.
Correct.
Wow. So who knows what could occur
Well, we can model some things.
environments.
So you can run different rules, but it's very computationally intensive.
Huh. That's why when people talk about aliens, right? They hypothesize that there's a possibility that we wouldn't even be able to understand or be able to communicate or, be able to really comprehend what an alien is or what alien's doing if they come from a dimension with a different set of rules. But if they did come from another dimension with a different set of rules, how would they be able to present themselves in like our dimension or our universe when we follow like a completely different set of rules? You know what I mean? Like so many things would have to be taken into account.
Yeah. So when you say dimension, I'm like, I think I know what you mean, but I don't think you mean dimension. I think you mean a different rulal multi-way system, a different universe, so to speak.
Yeah.
All right. Yeah. So it's not a dimension. Yeah. It'd be a different universe with different rules. And so if we're not causally connected, then to our understanding, there wouldn't be a way that they could, right? But if within our universe, they existed in a different place in rulal space, right? Then there would have to be a translation language between us and them. And there should exist one. It just might be very difficult.
Okay, so they wouldn't be like under a completely different set of rules, because if we think of category theory, there would be some overlap between their set of rules and ours, which would give them the opportunity to enter our set. Is that essentially
not so much an overlap, but a translation language between the two.
I see. Yeah, so it just wouldn't be so. It could just be like a really far distant category of, or like aliens with such a different set of rules that would be able to come into our space, because it would just be
different rules,
too different with too many different rules, and it'd be impossible to complete or endure.
So think about it like, there's people on the planet that speak different languages, right?
Yeah.
So if you don't know the language, you don't really know what they're saying. But there exists a translation between the language you speak and the language that they speak, and you can learn that, right? It just takes effort, time and effort. But the reason that that's possible for us and with other people on the planet is that we have shared context, right? We have a shared causal history as well. And so it kind of, it seems as if that's sort of required for you to be able to have a translation language. You have to share some sort of context. And so if we don't share a context with aliens, then we're fucked, essentially.
It'd be so funny for aliens to come and they're unsure how to communicate with us as well. So they're just doing hand signals, or they're trying to sell us something. That
implies that they have hands, guy.
Right. Well, whatever they might have. I don't know. Yeah, you're right. They'd be attempting to do some sort of signaling to communicate with us. Or it'd be so funny if they busted out a calculator like they do in Thailand. When you go up to a vendor in Thailand and you're bargaining for a price of something, and the Thai person just puts the number of baht that they want for the product, and they just hand you the calculator so you can begin bargaining with them on the calculator.
Yes,
it's so funny, right? It feels like the exact same thing with the aliens.
So it's kind of like if there probably are other things out there in rulal space, right? In the different rulal multi-way systems, but whether or not we could interact with them or that they could ever get to us or any other thing, I don't know. I don't think it seems plausible based on this. I think that we sort of only have a hope of doing it with things we have a some sort of shared context or causal history with, if that makes sense. So we've sort of all evolved on this planet. So we share context, we share a causal history, which is why we can communicate, which is why we can do all of this. But if something is completely disconnected that isn't causally related to us, then I don't think that we can. I don't think there will be an ability to communicate or even interact. I think it's just two completely different things. But at some, maybe through time and through all of that evolution, there might be some sort of merging that happens, right? So different rulal systems might lead to one sort of path, and then we're going down another path. And for most of the time, we're disconnected, but at some point we merge. That could be possible.
Could there be a sort of accidental merge that could occur that could affect the rules of our space?
Wait, what do you mean accidental? Like, could something happen that the universe wasn't meant to do?
Yeah, like imagine, because if we go back to category theory, right? And we have two sets that are sort of overlapping in rules. I know I'm not saying it correctly. You can sort of try and say it better than me. But anyways, so there's some overlap with the rules, right? But some of the rules from this set somehow get into this set over here. Like there's like this accidental merge, and we'll take gravity, for example. Gravity from this universe enters our universe and suddenly affects the gravitational pull of our Earth, for example. Something ridiculous.
Look, maybe, right? The one thing that I was thinking of when you were saying that is like, so say you have these different rulal multi-way systems and think of them as universes, right? Maybe there could be some sort of collision, right? So you say you have a big universe doing its thing, you have another universe doing another thing, and they sort of collide. Maybe that could happen. Maybe something like that, and that could have some sort of effect in our universe that we would have, like, that would seem strange to us, that would seem wrong, that would seem like an accident or seem like something, what the hell? That wasn't meant to happen in our universe. It can't be explained. I think that might be a possibility.
Yeah, I think I'm still...
You go.
I keep leaning on this like dimensional thing. Like each time I'm trying to envision how this is occurring, I keep going back to, I just keep leaning on this dimension thing. I think that's where I keep getting it wrong when I'm trying to like figure out how this actually works as my brain is melting. And I need to sort of get away from that, because it's not as if like two dimensions are going to intertwine like that. I'm kind of looking at the concept wrong. But when you said one universe merging with another universe, I'm beginning to understand like a little better. Than it just seems like it's very unlikely that something like that would happen, because, well, actually maybe not, because we're traveling right now through space, and space is expanding, so we are going somewhere
within something.
Could we crash into another universe?
Maybe. I don't know enough about all of these things to definitively say no or yes. So I'll just quickly share a little screen thing with you. This is a Wolfram post.
Okay.
And this is the concept of the Ruliad, the entangled limit of everything. So just imagine that, like, our universe exists as one of these points within this greater space of other universes that are completely different to ours, completely different rule systems, completely different laws of physics, et cetera, et cetera, et cetera.
Right. Okay. And here we are, one of these blue points, these blue nodes traveling through space. Looks like we're pretty close to other nodes, guy. Looks like an accident might happen at any time now.
And so, but would it be an accident, or would it just be a natural process?
Good point. It would just be a natural process.
Right? It's freaky stuff. Okay. So I want to get into causality and causal relationships as the last sort of bit for this. So one thing that Gerard's done is come up with a new formalism for causality, right? And it's pretty damn good. It encompasses so many. So it's a very abstract, obviously, but because of that, it encompasses all of the formalized versions of causality that we have across many different things, or across many different systems and across many different scales. So his core idea is that if two sequential computational processes, so two processes running in sequence or parallel, right? Sorry, if a sequential computational process, so one sequential thing, so one series of steps cannot be parallelized, right? So you can't take that one series of things and turn it into two and run it in parallel, that it implies a causal relationship between them. So, for example, consider a single cellular automaton, right? So we've looked at cellular automata before, with rules that propagate a signal forward at each step. So if we observe two states, A and B, where B occurs after A in the sequence, we cannot parallelize them because B relies on the signal from the prior state of A. So there's an overlap between A and B. Yeah. This suggests that A causes B. Very basic, right? Very simple, super like later. So you can illustrate it graphically. So if you depict the automata sequence as a zigzag path, there is no way to straighten out the zigzag into two parallel lines, since the steps depend on each other. This obstruction to making the sequence parallel is the manifestation of causality. Yeah. So another example, we could take two computational processes that occur in disconnected parts of a grid, so no signal can propagate between them. Here, the sequences A and B can be parallelized into independent straight line paths since they don't interact. Lack of an obstruction to parallelism implies no causal link. And in category theory, you can formalize obstructions to parallelism as the inability to unroll sequential tensor products into standard Cartesian products. The dependencies must be respected. This formulation encompasses various specific causal modeling formalisms as special cases. So the brilliance of what Gerard's definition does, using parallelism as a bridge between computation and causality, causal relationships arise precisely when parallel/concurrent computing is obstructed. So it's very simple, but very profound at the same time.
Okay.
So in this whole thing, we've got more that we can cover, but we'll do this in another app. We've got computational irreducibility, multi-computational irreducibility. We've got to talk about tokens and global multi-way systems and a whole bunch of other structures. But essentially what he did in his talk, just for me to summarize, is he showed that at the base level, you have like algebra, right? You have like this, a one category, okay, which is just it's an algebra for how things compose together, how objects compose. You can build up this structure. And if you do it in the infinite limit, you end up with this infinity groupoid, right? And that infinity groupoid limits to like a three-dimensional space, so to speak, right? It gives us general relativity. And that within that, we just pause for 1 second, I got to do a wee. So the beauty of what Gerard does in the lecture is he shows that how you can start with these very simple things like an algebra, right? How objects and processes compose, okay? A one category. And then you can do levels of abstraction. So you can, from the one category, you can go to a two category and a three category. And if you do this in the limit, you end up with one of these infinity groupoids. Okay, so at the base layer, that basic algebra, right? The processes and how they compose sort of models quantum mechanics. At the 2 category, you kind of get quantum field theory. And then if you do it in the limit, you end up with like general relativity. Okay. And he links this to 2 different ways that we sort of have of looking at the universe. We can either look at it from top down, right? A constructivist view, or we can look at it from, bottom up, a constructivist view, right? Or we can look at it from top down. Yeah. So we have these 2 sort of ends, exactly, or both, and understanding how they both relate to each other and how one can do the other. But they show with the Wolfram model is that you can start with very simple things and build immense complexity, and how from that, the things that we observe and the measurements that we make and the predictions and all the rest of it arises. And I think that it is truly beautiful. He has a fantastic way of articulating these things. And we will go into more detail with all of this. And he does finish the talk with a pretty mind-blowing way of sort of thinking about things and framing things. So a couple of the implications, right? So the fundamental laws of physics, like general relativity and quantum mechanics, emerge from consistency conditions of the space of possible computations. It suggests reality is fundamentally computational. And so that's what they're sort of showing with this. And the fact that different observers can experience different effective laws of physics based on how they partition the causal multi-way systems, right? Which sort of allows for a reconciliation of relativism with realism, which is like an age-old sort of debate, right? He also frames, so when I just said about the building it up from the bottom, starting with the algebra, the process and how they compose, or looking at from the top down, that infinity groupoid perspective. So he sort of has this thing, he frames the debate between rationalism and empiricism in terms of how computational burden is divided between observer models versus reality. So it blows my mind. It's just fascinating.
I feel like the direction of this, as Wolfram and Gerard keep advancing in this field, is going to get to a point where they're just going to sneak in God. It's going to be like, and God. I feel like.
Okay, so I'll give you my take. This is what I think God is. Historically, when people have spoken about God and religion, or gods, right? I think that that's really what they might have been trying to refer to was the infinity groupoid, the Rulliad, right? And then because God created all of us. Well, that's true in a sense, because without this infinity groupoid, we couldn't exist. And I think when people talk about the universe, that's what they're like, that's what this shows, is that the universe is an infinity groupoid, or is a Rullian or multi-way system within an infinity groupoid, which exists within the infinity one topoi. So the universe can exist in a space of other universes, and we're just one universe in a space of many different universes.
Yeah. And at the fundamental level, it's all computationally bound. That almost sounds like then there's a creator or something. You know what I mean?
No, so think, the way I sort of think about it, and I don't know if this is exactly correct or not, is more that any existence is the default, right? So anything that can be, happen, is, whatever, is. Anything that can be, any formal system, any series of rules or ways things can combine or not combine or whatever, is. And then we just exist as some subset of that, and we get to experience a subset of that. So It's a pretty different way of thinking about things. But at the end of the day, if you assume that existence is the default, then it takes away all the confusion. It's just like whatever can be is. Whatever could possibly happen, can possibly happen is. And we exist as a subset of that. And we have some freedom, we have some degrees of freedom to experience different aspects of that. And the choices that we make, the actions that we take, allow or change those degrees of freedom and allow us to experience differences within that, the different possibilities within that space.
Wolfram, his last dying breath, if he hasn't figured it out yet, it's fucking God, man. It's fucking God.
Well, honestly, that's the connection that I made. And it makes sense to me when you think about like ancient civilizations and what they were doing when they were trying to think about these things. And it seems like referencing the universe as God, and the reason they described it as being a person was because that was the only way they could relate it to people back then. Like the people might not have had the capacity or the ability to conceptualize these abstract concepts as much as we do now because of computers and computation and the growth of knowledge. Whereas back then, the easiest way was to say it's a guy in the sky, right? Because then people can imagine what a guy's like. Can you imagine trying to explain what an infinity groupoid is to somebody 5,000 years ago?
Or an idiot?
Exactly, right? It's almost impossible today, let alone back then. So you see how these sort of the stories emerge as sort of, low resolution translation languages or ways of translating things over a shared context, right? People grew up around other people, they evolved around other people, so they knew what people were. So referencing God as a person makes it relatable.
So, Rubes, you definitely got me hooked on the subject matter for sure. Even though I didn't say very much today, I was listening. I'm hoping during the editing, I'm going to pick up a little bit more of what you were saying. And I like that we're going to continue this because this is a really dope ass topic. And hopefully I can, get up to some higher levels, expand my knowledge on this a little bit more so I can participate a little more next time. But that was good, guy. Well done.
Yeah, thanks. And thanks for participating. It's I learn a lot by trying to do this because it helps me understand what I'm missing, what I don't know, what I need to further develop within myself and my understanding. The whole goal of all of this is we'll do a series of these that sort of dig decently deep and try and explain things in simple terms so that we can do one final episode of this where we sort of explain the totality of it and the implications, like how we go from how it goes from this low level all the way up, and then what that means and what the implications are for science and life and existence and the meaning of life and all those other things. So we can do a whole video on that. But because it's so dense in domain-specific language and concepts, you sort of have to go over these things to develop some level of understanding so that we can then use that some level of understanding to go through the all-encompassing final episode, so to speak. But we'll link to the lecture that Gerard gave. I'll also provide some notes in the description as well that people can read through to help further develop their understanding. And it will be an evolving document where we'll continue to add, like examples and definitions for things and try and relate it to people in just simple terms, right? Like it helps me with my understanding, trying to relate things in simple terms. I'm not real good with the jargon initially. It takes typically a long time for me to learn it.
I hear you, guy. So what about the first take? Nothing from there that you like to post, or what if people ask for it?
Well, if people ask for it, we can. But I don't know. We went off on different tangents, I think.
Yeah, we did. Maybe I could just take our tangent that we talked about for the most part and post that so people can see what we talked about.
Yeah, potentially. I'll watch it and I'll let you know.
All right,
Guy. We'll call it a wrap. Thank you very much.
Don't forget.
Hey?
I was just going to say, the best way to let us know that we're complete fucking idiots is by subscribing to the channel, liking the video, and also sharing the video with your arch nemesis. Arch nemesis.
Yeah, people you hate. Just annoy them with our idiocy.
Fuck yeah.
Thank you very much for watching. If you have any questions, put them in the comments. Otherwise, have a lovely day, morning, afternoon, evening, or night, rest of the week. Peace. Love you, guy. Bye.
Love you, bro. Peace.